6,371 kilometers beneath you, there is a solid iron sphere larger than Pluto. It spins independently from the rest of the planet, and recently, it may have stopped. No human has ever seen it. No drill has come remotely close. Yet everything about why Earth remains habitable, why we have not become a dead, atmosphere-stripped world like Mars, traces back to this one hidden object. The question is not just what is down there, it is how anyone ever figured it out. Imagine peeling back the planet, layer by layer, to reveal a hidden world defined by numbers as precise as any map. The journey begins at the surface and plunges through the crust and mantle, reaching a boundary at 2,891 kilometers below your feet. This is the core mantle boundary, a sharp divide where solid rock gives way to a vast ocean of molten iron and nickel. The liquid outer core extends downward for another 2,259 kilometers, a restless, churning layer that makes up nearly a third of Earth's total volume. But even this is not the end. At a depth of 5,150 kilometers, the liquid yields to something even stranger, a solid sphere of iron and nickel, the inner core, with a radius of 1,221 kilometers. Though it occupies just about 1.5% of Earth's total volume, this sphere is the planet's deepest anchor. Each of these boundaries is invisible, yet their locations are known to within a few kilometers, thanks to seismic measurements and global models like PRIM. The numbers themselves are stark: 2,891 kilometers to the outer core, 2,259 kilometers of liquid metal, 1,221 kilometers of solid heart. Yet they trace a roadmap to Earth's center, setting the scale for every scientific question that follows. No instrument has ever crossed these boundaries, but their reality is as certain as the ground beneath us. What happens to a wave when it strikes the unknown? Earthquakes send out two main types of seismic waves: P waves, which compress and expand the ground, and S waves, which shear side to side. P waves can travel through both solids and liquids, but S waves need the rigidity of a solid. At first glance, this difference seems subtle. In practice, it draws a sharp line through the planet. When a major earthquake shakes the crust, seismographs around the world record the arrival times of these waves. Yet, at certain angles, specifically beyond about 106 degrees from the quake's epicenter, S waves simply vanish. No signal, no trace. The explanation is as stark as the data. S waves cannot cross the liquid outer core. Their absence draws a global shadow, a silent testimony to a world of molten metal hidden beneath our feet. P waves, in contrast, do make it through the liquid, but not without a twist. Between 104 and 140 degrees, stations fall into a P wave shadow zone, where direct arrivals are missing or dramatically weakened. The reason is refraction. As P waves hit the core mantle boundary, they bend sharply, carving out a region where their paths cannot reach. This shadow is not a guess, but a precise geometric fingerprint. Its size and shape allow scientists to calculate the core's depth and extent. This turns the absence of a signal into hard numbers. The geometry is so exact that it leaves little room for doubt. A vast liquid layer lies between the solid mantle and the even deeper solid heart. The next puzzle is what lies within that heart, and how a faint signal inside the P-wave shadow zone would change everything. In 1936, a Danish seismologist named Inge Lehmann sat alone with stacks of paper seismograms, searching for answers in the restless lines drawn by distant earthquakes. At the time, the prevailing belief was simple. Earth's core was a single, undivided liquid sphere. Yet Lehmann questioned what others had missed. She noticed something odd, a faint early P-wave signal appearing inside the P-wave shadow zone, a region where, by all known rules, no direct arrivals should exist. This signal, which she labeled P', arrived just a few seconds sooner than theory allowed, and its delicate trace was easily lost in the noise. Lehman's insight was both methodical and bold. She compared the travel times of these anomalous waves with predictions from every possible model. Only one explanation fit. There had to be a solid sphere at the planet's center, denser and faster than the surrounding liquid. The P-prime waves, she realized, were passing through this hidden heart, traveling faster through solid iron nickel than through the liquid outer core, then re-emerging where no one expected them. Her 1936 paper quietly rewrote the map of the planet. The solid inner core, with its higher seismic velocity, was no longer a guess, but a measured reality. Lehman's discovery, born from patience and a refusal to accept easy answers, proved that even the faintest signal can expose the architecture of a world we cannot touch. In that moment, the deepest layer of Earth was revealed, not by digging, but by listening. Measuring the spin of Earth's inner core demands a kind of patience and precision few fields require. Seismologists rely on the planet's own tremors, earthquakes that send P waves racing through the globe. Some of these waves, known as PKYKP, cut straight through the inner core, while others called PKIKP skim its surface. By comparing the arrival times of these waves at seismic stations scattered across continents, researchers can detect shifts as slight as a fraction of a second. The real breakthrough comes from tracking repeating earthquakes, called doublets, that rupture the same patch of fault years apart. These allow scientists to isolate changes in wave arrival times, revealing the inner core's slow drift beneath our feet. After decades of careful analysis, a consensus has emerged. The inner core rotates eastward at about 0.1 to 0.5 degrees per year relative to the mantle. This is not a fixed rate. Some studies hint at periods of slowdown, even brief reversals. Another method, normal mode splitting, listens for the Earth's free oscillations after massive quakes. These oscillations, especially those sensitive to the deepest layers, confirm the rotation rates found through PKIKP timing. Agreement between these independent techniques is rare in geophysics, lending unusual confidence to the result. Even so, the signal is faint, always at the edge of what can be measured. Mantle complexity and limited station coverage blur the picture. Yet the best estimates hold. The inner core's rotation rate sits between 0.1 and 0.5 degrees per year, a baseline for whatever changes may come. What if the very heart of our planet, long thought to spin with steady purpose, was suddenly found to stall, or even reverse? In 2023, a new analysis shook the scientific world. Seismologists gathered decades of earthquake data, not just from a handful of events, but from tens of thousands, spanning continents and generations. Using a stacking algorithm, they layered seismic recordings, PKYKP waves that had pierced the inner core, on top of one another. The goal was to amplify the faintest signals, to listen for a whisper beneath the roar of the planet's daily noise. The result was not what anyone expected. For nearly 30 years, the prevailing wisdom had held that the inner core spun eastward, drifting ahead of the mantle by a fraction of a degree each year. But the stacked data told a different story. When the numbers appeared, the measured rotation rate was nearly zero. In the most recent decade, the trend even dipped slightly negative, a hint that the core's motion may have reversed, if only for a brief moment. A pause here, to let the implications settle. The deepest engine of Earth, once believed to turn with unwavering regularity, might in fact hesitate, slow, or even turn back. The uncertainty is not a flaw, but a revelation. The inner core's behavior is more dynamic, more unpredictable than any model had dared to predict. As one seismologist put it, our planet's heart may be beating out of step. This finding does not just rewrite textbooks, it opens new questions. What force could bring such a massive iron sphere to a near standstill? And what does this mean for the rhythms of the planet above? The search for answers now moves from seismic signatures to the invisible hands, magnetic and mechanical, that grip the core and set it spinning, or bring it to a halt. What invisible hand grips the heart of the planet, forcing it to spin, or at times, to hesitate? At the boundary between the solid inner core and the swirling liquid metal of the outer core, two rival forces wrestle for control. The first is electromagnetic torque. Here, the inner core's iron lattice conducts electricity, and the planet's magnetic field threads through both the solid and liquid layers. As the outer core churns, it drags magnetic field lines along, creating Lorentz forces at the interface. These electromagnetic torques can nudge the inner core to rotate faster or slower, depending on the strength and direction of the geomagnetic field. The effect is powerful. Numerical models show that, with a field strength of about 25 microteslas at the boundary and iron's immense conductivity, the magnetic torque should dominate. Yet, the true magnitude remains uncertain, hidden behind the veil of unknowns in field geometry and core conductivity. The second contender is mechanical coupling. The inner core is not a perfect sphere. Its boundary is dimpled and rough, with topographic bumps rising meters high. As the liquid outer core flows past, it tugs on these irregularities, producing a viscous drag, a frictional torque that can slow or speed the sphere. While this mechanical grip is real, calculations suggest it is far weaker than the electromagnetic handshake. Still, the precise topography of the inner core boundary remains poorly mapped, leaving room for surprises. Both forces operate in tandem, but the evidence points to the magnetic torque as the main driver of the inner core's changing spin. This interplay of invisible forces grounds the mystery in physics, setting the stage for the next question. How does this deep struggle shape the shield that protects life at the surface? What keeps a compass needle pointing north? And what would happen if that invisible force faded away? The answer begins far below our feet, in the restless ocean of liquid iron and nickel that forms Earth's outer core. Here, at depths beyond 2,900 kilometers, heat escaping from the solid inner core stirs the metal into motion. This is no gentle simmer. The temperature difference between the core's boundary and its center drives powerful convection currents, rising and falling in columns shaped by Earth's rotation, a phenomenon known to modelers as the Coriolis effect. These swirling flows of molten metal act like the coils in a dynamo, generating electric currents that produce the planet's magnetic field. Supercomputer simulations recreate these turbulent patterns, revealing how even small changes in heat flow or composition can alter the field's strength and structure. As the inner core slowly grows, it releases not only heat, but also lighter elements, adding another source of buoyancy that fuels the churning. The result is a magnetic shield that stretches from pole to pole, protecting the atmosphere from solar wind. But this planetary engine is not eternal. Since the 1840s, systematic measurements from observatories and satellites have recorded a steady decline, a drop of 10% in the field's strength. The cause lies in the subtle balance of heat, composition, and flow deep within the core. As the engine slows, the shield weakens, raising questions about the future of life's protection on Earth's surface. How long can the planet's magnetic shield hold its ground? The record is written not in words, but in the orientation of ancient minerals, tiny compasses locked in stone. These paleomagnetic strata reveal a pattern. On average, Earth's magnetic field flips polarity every 200,000 to 300,000 years. Yet the last full reversal, known as the Matuyama-Brunhes event, took place 780,000 years ago, a gap more than twice the usual interval. By the numbers, the planet is overdue. Signs of instability are not confined to the distant past. Today, The magnetic North Pole is moving at a pace of nearly 50 kilometers per year, racing from the Canadian Arctic toward Siberia. This drift, tracked by global magnetometer networks and the International Geomagnetic Reference Field, unfolds far faster than the slow wanderings of earlier centuries. Meanwhile, high-precision atomic clocks and satellite laser ranging record subtle changes in the length of day. Variations of just a millisecond are enough to betray the shifting flows deep within the core. These clues point to a restless engine beneath our feet, one whose cycles are measurable but unpredictable. The cadence of reversals, the accelerating pole drift, and the minute adjustments in Earth's rotation all suggest a system nearing a threshold. The present is not an exception, but a chapter in a geologic rhythm that stretches back millions of years. In this context, Earth's magnetic field is not a static shield, but a living, breathing phenomenon, one whose next transformation may already be underway. What would happen if Earth's magnetic shield faltered or vanished? To grasp the stakes, look to Mars. Billions of years ago, Mars too had a molten core and a magnetic field. But as its inner dynamo sputtered out, the shield faded. Solar wind, a relentless stream of charged particles from the sun, slammed into the unprotected Martian atmosphere. Over millions of years, molecules were stripped away and lost to space. Today, Mars is a cold, barren world, its thin air unable to support liquid water or protect against radiation. On Earth, the story is different. Our churning outer core, powered by heat from the solidifying inner core, keeps the magnetic field alive. This invisible force deflects most of the solar wind, preserving the atmosphere and making complex life possible. Without it, oceans would slowly boil off, and the sky would be scoured thin, just as happened on Mars. The difference between a living planet and a dead one lies in the physics of a hidden engine, 6,371 kilometers below the surface. Every compass, every breath, every living thing owes its survival to a process no one has ever seen. The magnetic field is not just a scientific curiosity, it is Earth's shield, and its fate is tied to the restless activity of the core. The stakes are planetary, written in the silence of Mars and the vibrant blue of home. What does it mean to call the center of Earth a solid sphere? Imagine matter compressed so tightly that iron atoms are forced into an orderly lattice, each one locked in place by pressures reaching 360 gigapascals. The inner core is not a molten sea, but a dense alloy, about 80% iron, 20% nickel, where atoms arrange themselves into a hexagonal, close-packed structure. This is a world of perfect regularity, invisible and unreachable, yet its properties are revealed through experiments that mimic the core's extremes. In diamond anvil cells, researchers like Dr. Anna Martinez have watched tiny samples of iron-nickel freeze at 5,600 Kelvin, confirming the hexagonal close-packed lattice predicted by seismic models. But the inner core is not a relic. It is growing, grain by grain, at a rate of about 1 millimeter per year. Each new layer releases latent heat, fueling the dynamo that powers Earth's magnetic field. The process began between 1 and 1.5 billion years ago, and it continues today, a silent, relentless construction project at the heart of the planet. How do you study a world sealed beneath thousands of kilometers of rock and metal? The answer lies in a global network, more than 150 seismic stations listening for the faintest tremors. Their recordings pooled and compared across continents. Each earthquake is a probe, each arrival time a clue. But seismology is only the beginning. In laboratories, diamond anvil cells squeeze tiny samples of iron-nickel alloys to pressures of 360 gigapascals and temperatures above 5,700 Kelvin, recreating the inner core's ferocity on a microscopic scale. Here, researchers watch crystals freeze and shift, searching for signatures that match the signals from deep below. Yet even these tools have limits. New approaches push beyond. Machine learning algorithms sift through noisy seismic data, spotting patterns invisible to human eyes. Experimental neutrino tomography hints at mapping density with particles that barely interact with matter at all. And still, questions multiply. Some seismic studies point to an innermost inner core, a distinct 300-kilometer-wide region with different crystal alignment, hidden within the solid heart. No one can say for certain if it exists, or what secrets it holds. The journey to 6,371 kilometers is unfinished, each answer opening new mysteries, each tool revealing how much remains unknown. Beneath our feet, an iron heart turns, unseen, yet essential. As Earth's magnetic field wavers and solar storms intensify, our survival depends on mysteries we still struggle to decode. We may never witness the core directly, but its silent influence shapes every breath we take. In a world built on surface certainties, the greatest frontier may always lie beneath. What question would you ask Earth's core? Share your thoughts below.